Hey guys, just give us about say 2 minutes. We'll just wait for a few more people to join and we'll get started. I don't expect a huge turnout because it's about 7 p.m. on a Thursday, but we'll see who can make it. Otherwise, the recording will always be available for you. So you can always catch it on, I think, Prof. Ben's YouTube channel. So yeah, just give us about like 2 minutes for more people to join in. Just checking. Y'all can hear the audio well, right? Just give me a thumbs up if it kind of works out. All right, great. Thank you. Okay, to all of those who are here, thank you so much for making it. I know that it's kind of late in the evening, so we'll try to keep this short and as explanative as possible. Uh, So yeah, welcome to the Backprop Bootcamp. It's kind of like a quick 1 hour workshop on, learning backpropagation from first principles. We'll be looking at a whole lot of fundamental concepts that you need to know in order to do backpropagation well and to do it easily without any hassle or pain. So in terms of a quick overview of what exactly we're going to cover, uh, we will be starting off with learning about this thing called a computation graph. Whenever we have a bunch of operations being done in a sequence, we create this thing called a computation graph, and you can perform a whole lot of operations on this graph. And we're going to see that very soon. Next, we're going to cover some basic calculus, multivariable calculus. I'm going to motivate single variable calculus and then show you how your regular differentiation can be taken one step higher to partial differentiation, which we use in the multivariable context. Excuse me. So next, we're also going to be looking at the chain rule, another very important concept within calculus. And once we kind of settle down with both of these, we're going to go into backprop fully. And once we cover backprop theory, we'll look at some examples, some worked examples. I'll be doing it by hand. There won't be any math on slide situation happening here. So I'll be giving you a walkthrough, kind of like a live demo on how to do backprop on a single perceptron or a single neuron, a single layer, and even a 2-layer neural network. Let's keep it very simple, just for you to get the higher level concepts. And I guess one thing that the teaching staff from 2109S, the one question we receive a lot is how do you backpropagate weird functions like ReLU, right? Because it has a kind of conditional forward pass, whether it's a 0 or 1. We're going to look at all of that in detail very, very soon. So let's get started. let's begin by talking about a computation graph. And before that, at any point in time, if anybody has any questions, please feel free to unmute or use the chat. I have both the chat and the kind of the participants list. So anytime, please message me or kind of voice out. Okay, let us begin. What exactly is a computation graph? I mean, before we even get to that computation bit, what even is a graph, right? From CS2109S, you would have learned that a graph consists of nodes and edges. You draw nodes as circles, and edges are kind of the lines connecting them. These graphs represent relationships between nodes, and you can represent a whole lot of things using these graphs. And in this case, in the whole context of machine learning, we'll be using computation graphs to show us what kind of operations we're doing and to what variables and what's being used. So when we compose functions together, we create these structures called computation graphs. So let's say we have a bunch of functions and let's kind of represent them as variables, right? Let's say that variable C, it's the sum of B and A. Next, when we want to get this variable E, it's the product of D and C. And finally, let's say we want to get this variable F, which is just 3E squared. Sure, we can write it as variables, but it would be more compact, more representative to write it as some generic function, right? So if we had to write it in function form, C would be some function G of A and B, and which is basically the sum function over here. Next, E is the function H of D and C, which corresponds to this product over here. And finally, F is a function J of E, which is this 3E square operation here. So what we've done so far is we've taken this variable form of equations and we've converted them into some functional form of variables using these functions G, H, and J. Now, let's represent these functions in this thing called the computation graph. And in the computation graph, functions, so this G, H, and J, they're represented as nodes. And all these variables like A, B, D, C, E, they're all represented as edges. So if we had to take these bunch of functions and convert it into a computation graph, it would look something like this. As you can see, functions G, H, and J, they are nodes. And all these variables like A, B, C, D, they are the edges of the graph. So we can represent it in some form like this, where we take in A and B, we kind of put it through function G to give us C. Next, E and D. Next, we pass E through function J to get this variable F. So you can think of it as a left to right flow between the variables. They're passing through this computation graph and out comes the output F. So yeah, this is a computation graph form of this function right here. Next, let's talk about partial differentiation. So what my approach for this workshop will be is I'll teach you these individual components, and after that, let's put them all together to learn how backprop happens in neural networks. So the first component I showed you was the computation graph. The next component I'll be showing you is partial differentiation. And before we get there, let's talk about gradients. What is a gradient, right? Let's talk about it in the context of the straight line. We've all seen the straight line from middle school. It's this thing over here, this M. It represents the slope of the line, how slanted it is. And of course, you also have this thing called C, which is the vertical intercept, but that's not really important here. What the main focus is this variable M, which is the gradient of a line. we can kind of take one step forward and kind of show it in the context of a curve. We've seen it in a straight line. Let's look at it at a curve. What exactly is the gradient of a curve? We can't really come up with a single gradient for the curve because clearly this area is very flat, but then this one is very slanted. So different parts of the curve have different gradients. And to compute this gradient, this general form, we resort to using basic differentiation, right? dy dx. We've all done this in high school in some way or form. So if I have this y equals x square function over here, if I had to get the gradient of it, I would simply differentiate this to get dy dx, and it would give me this final output of 2x, because the two kind of comes down, and by the laws of differentiation, it gives us a 2x. We all know this. Now, so far, this y equals 2x, we call it a univariable function. This term uni, it means single, it means one. It means that only a single variable x is being used in the computation, which is why we can clearly write it in the form of y equals fx. I only have one variable x. If we kind of abstract it higher to kind of like one step higher, we get multivariable functions. And these are functions that take in many variables, right? We've gone from one over here to two over here. And of course, you don't need to stop at two. You can all the way go until 100 variables, 1,000 variables, depending on how complex your function is. So over here, we have z is a function g of x and y. That means z would be some function of x and y, right? Maybe x squared plus 3y squared, for example. So when we calculate gradients in this univariable function, we're looking at the rate of change, right? The rate of change of y with respect to x. So if by a bit, the gradient tells us that. But in the multivariable setting, you have so many things changing. You have all of these variables changing. X could change, y could change. X could remain constant, y could change, and x remains constant, right? So many different combinations. And because of that, we can't just compute a single gradient. There's so many gradients that we can compute. And for that, we use this thing called partial differentiation to compute the gradients of z with respect to x and the gradient of z with respect to y. So two different gradients because I have two different values that are changing. So we aim to compute the rate of change of z with respect to x and the rate of change of z with respect to y. And we do this by calculating this thing. This is the partial gradient of z with respect to x, and this is the partial gradient of z with respect to y. Originally, we were dealing with this thing called dy dx, but as you can see, now we're kind of having this very fancy curvy d over here, and you can simply pronounce it as dou, right? You can say dou z dou x and dou z dou y, right? It's kind of confusing. It's a mouthful. So for the sake of the remainder of this presentation, I'll simply be using d over here as we regularly do. But do understand that in your exams or whenever you're dealing with multivariable functions, you always need to write gradients using this dou symbol right here. So yeah, I'll just be using d for the sake of simplicity. It means the exact same thing without loss of generality. So there are two different things or two different gradients we can compute. And to do that, let's say that we are computing the gradient of z with respect to x. So we're computing this guy right here. So if my target variable is x, what I need to do is I need to treat my y constant. Or if there are many other variables, I need to treat everything except x as a constant. Similarly, if my target is y, suppose I'm computing this guy, if my target y is y, then I have to treat everything except y as a constant. And let's kind of look at it practically. What exactly do I mean by treat it like a constant? Let's say that we need to compute dz dx and dz dy, and we're given some function z, which is, z of x and y, which corresponds to this formula right here. Now, if I want to compute dx dz, I told you before that we need to treat y constant. That means as if, and what happens to constants in differentiation? They get dropped, right? It's as if they never existed. We remove them and we just kind of ignore them when we are dealing with constants in differentiation. Similarly, over here, since we're treating y as a constant, I can ignore y, I can drop it. So it's as if this guy right here never existed, and all I'm looking at is this 6x cubed. It was as if I'm saying z equals 6x cubed. And that means my gradient dz dx is simply the differentiation of this univariable function. So we've taken a multivariable function or a two-variable function xy. We've kind of collapsed it into a single variable function of x. And 6x cubed, when you differentiate it, you'll get 18x squared. It's pretty straightforward. Now, let's look at dz dy, right? I'm going to remove all of these annotations. And now let's kind of do it with y as the target. And I mentioned above that when the y is target, I need to treat x as if it's a constant. So it's as if this guy right here never existed in the first place. So it's like saying z equals 3y squared. And that means dz dy is simply 6x because we're differentiating this formula right here. Pretty straightforward. And now we have two gradients, dz dx and dz dy. So that's the respective rate of change of z with respect to either of these variables. Had some 100 variables, right? So x1, x2, all the way till some x100. That means since I have x variables, I'll have to have x gradients. That means dz dx1, dz dx2, all the way till dz dx100. And you can, of course, do this as we've done so above. When we're differentiating this, all of this fails to exist. And then when we're differentiating x2, this doesn't exist and this doesn't exist. None of this exists either. And finally, when we're differentiating with respect to x100, none of this exists, and we're just looking at this single x100 variable right here. So that's how you do partial differentiation when it comes to these multi-variable functions. So that's one more component that I've taught you. So far, we've looked at computation graphs. Next, we've looked at partial differentiation. And finally, let's move on to the final component, chain rule. So we call it the chain rule because it's as if we are chaining these functions together. So if b is some function of a, and then you take b and you pass it here, and c is a function g of b, then you take c and you dump it here, and g is a function h of c, it's kind of like they're all holding hands, right? It's as if they're all clumped together like an actual chain. And you'll see why we actually call it the chain rule very soon. So I'll get to that very shortly. So let's assume that we have these three univariable functions. Of course, you can generalize this to multivariable, but let's keep it simple for now. If I want to calculate the gradient of g with respect to c, I just need to differentiate this function h, right? And according to high school math, that's saying I want to get h prime. My h prime is the gradient dg dc. Pretty straightforward. Now, what if I want to get the gradient of c with respect to b? Same thing, high school math tells us that I just need to get g prime, the gradient of the function g. And similarly, what if I wanted to get the gradient of b with respect to a, right? All I have to do again is say dBdA is f prime, the gradient of f. Now it begs the question, we have all these kind of these functions, variables, everything. But what if I wanted to get the gradient of g with respect to a? We can't directly differentiate it, right? We can't directly say dg dA equals something something, right? We need to kind of go back through the chain of operations. We need to kind of hop from this operation to this, from this operation to this, until we finally reach this a. And to do that, chain rule is our best friend. So if I want to compute the gradient dGdA and dGdB, right, and based on this set of operations, I need to do this double hop or even like a triple hop to get there. What I need to do is use the chain rule, which I'll explain now. So here now I bring in the concept of the computation graph. Let's take the same exact equations and represent them as a computation graph. Functions will become nodes, and variables like B, C, G, A, they will become edges. So my final computation graph will look something like this, where, as I mentioned, all my functions are nodes, all my edges refer to variables over here. And originally, the question I asked is, how exactly do I calculate dGdA and dGdB? And to do that, all we need to do is hop back, take a few steps back along our computation graph. So that means if I am at some variable g, I first need to compute this gradient dg/dc over here. And that means that's like me hopping from here till here. Next, I need to compute the gradient of C with respect to B. So I finally get this dc/dB. And finally, I need to hop. So that's like hopping something like this. And finally, if I want to go all the way till this variable A at the top, I need to go from B to A and compute this gradient called dB/dA. And that's as if I'm jumping from here like that. And the final chain rule is taking these individual chain links, right? We call them chain links, right? And a chain link is basically this individual thing. This is what we call a chain link. And we kind of put them all together and we kind of get their products. So finally, if I actually had to calculate the gradient of dGdA, I'll have to go back through my computation graph. Originally, with these equations, we went forward. Now what I'm doing is, second, waiting for it to upload. Okay, yeah. So waiting for it to go backward like this. So dGdA is now a chain product of dG/dC times dC/dB times dB/dA, right? And if we had to look at it as fractions, even though this is kind of not the right way of looking at it, but if we had to treat them like fractions, it'd be like canceling these guys, right? And finally, you're left with dG and dA. But of course, we were working with gradients, not fractions. So it's kind of like an intuitive picture in your mind. So now let's extend this to a multivariable setting, shall we? We have these bunch of equations, f, g, and h, these functions, and we have a bunch of variables. And if we had to go down or forward through the computation graph, I take my variable A, I take my variable B, and pass it through G to get variable D. And finally, to get F, I pass it through function H, and of course, with this E over here. And now using the same exact chain rule, it begs the question of, okay, so we have these variables A, B, C, D, E, and F. Suppose I want to calculate the gradient of dF, dA. How exactly do I do that? And to do that, we need to go back the computation graph. We need to kind of go back. So that means doing this hopping process. So that means from F, I need to go back to D, and from D, I need to go back to C. From C, I finally land at A. And you need to kind of use the gradients that come along that path. So that means I use DF, DF, DD over here. Next, I use DD, DC, which is the thing here. And finally, I reach my destination of DC, DA. And using chain rule, I just get the product, and this is my gradient. And it's like saying something like H prime times G prime times F prime, but I only look at A and I only look at D over here. Because of course, multivariable, we also have a B and an E. We don't want to confuse that. So this is how you take the computation graph analogy of the chain rule, and you are given this very nice framework of doing this hop, this skipping process to get the gradient of one variable with respect to another, where it comes way behind in the sequence. For example, I'm computing the gradient of F with something like A that comes so many operations behind. So now let's do a kind of head count here on what we've accomplished so far. We've looked at the computation graph, we've looked at partial differentiation, and finally we have looked at the chain rule. And now from here onwards, we're going to use these three concepts and reinforce our understanding of backprop over here. And before I go on to the second segment of this presentation, I'd like to ask if any of you have any questions. Please feel free to type it in the chat or unmute, and we'll get to it. Maybe about 10 seconds. If there are no questions, we move on. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And it's okay if you are unable to ask your questions. We'll have a whole Q&A segment at the end of this presentation. So now let's get into the meat of the backpropagation chapter. We are, so this was the concept taught in the lecture by Prof. Ben. And what we're going to do is we're going to examine it in detail. Prof. Ben actually went through a worked example with all of you during the lecture time, but allow me to kind of break that down further and kind of go into the nitty-gritty details for you to understand what exactly is happening. Okay, so in any machine learning problem, you can kind of boil it down to something like this, right? I have a prediction, and I want to make this prediction by taking some input, and I want to pass this input through some model F. And theta over here, they refer to the parameters of the network. So that would be like your weights and biases. It doesn't matter how many there are. There could be 100 layers or even 2 layers, right? Doesn't matter. We can abstract the entire thing and write it as y hat equals f theta of x. That is the machine learning problem. Next, we usually pass these predictions y hat through this thing called a loss function or a cost function, depending on wherever you read it. This loss function, think of it as your friend in telling you how off your prediction is, how wrong you are in making that prediction. And we compare this prediction y hat with this thing called the label. And this label is usually known during training, right? So this could be a classification label where we say, is there a tumor 1 or there's no tumor 0, a binary classification. Or this label could be a real value, like the cost of a house, right? House price. So the label could be a real value like 1,056,029.32, right? You can do it in anything, but this concept of a loss function, this remains in supervised learning. And we all know what supervised learning is, right? The fact that we have labels, there is this form of supervision, and we use that to update the network. And we get this error E. And this is the thing that kind of tells us how off we are. It's a real value. So it's just like a single thing where E is an element of R, right? So it's a real value like 4.6, 72 point whatever, right? So what I want to tell you is, now that we've learned about computation graphs, I want to show you the conclusion that neural networks are computation graphs, or you can use a computation graph to represent a neural network, right? They're one and the same. So let's say we have this two-layer network, right? So this top part is layer 1, and this bottom part is layer 2. And of course, we have a bunch of parameters, theta, that we're trying to optimize. We have W1, B1, W2, B2. And of course, we have like these intermediate operations like activation functions, the equation of a line, the whole WX plus B thing, right? A whole bunch of operations. And this sigma over here, you know, this is a Greek symbol. FYI, it's called sigma. This sigma could be any activation function. Let's generalize it. It need not be sigmoid, which you've learned in the lecture. It could be any activation function. So what exactly we're doing is, let's take this very two-layer network as we've done it before. Let's represent it as functions. Let's abstract it one layer higher. That's like saying my forward pass of Wx plus B, it can be represented as this function F1. And on the other hand, again, the same thing of W2 A1 plus B2, which is the second layer, it could be another function F2. Doesn't matter what it is, let's just call it two functions. These bunch of operations, as you can see, we have functions, you know, sigma and F1, F2. And on the other hand, we also have variables, right? All of these guys over here. And that just makes it so fruitful to use a computation graph. And it would look something like this. We have our first layer L1, and we have our second layer L2, and out pops the prediction Y hat given some input X. And this is the computation graph, pretty straightforward. You perform your activations as normal. You do your forward pass, and you know, boom, you get a prediction here. Pretty straightforward, we know this. Next, let's talk about, so let's say we are working with this specific computation graph. And for the sake of this, to simplify this, let's zoom in on one of these nodes, one of these function nodes that take in some variables and output some variable, right? And of course, they're connected to some other components that come before and after. So let's zoom into one of these nodes in the computation graph. Let's say, you know, for the sake of the argument, that we have this series of functions. So X is some function G of Z, Y is some function F of X, and finally S is a function H. Okay, whoops, this is supposed to be Y, right? So S is a function H of Y. So let's look at it from a computation graph perspective. We take in this Z, we get X. We put in this X, we get this Y. We use this Y and we get out the S. Now, the question backpropagation gives us is, how do I compute the gradient of S with respect to Z, or any one of these earlier variables like X? And this kind of brings me to the concept of the different types of gradients there are in the computation graph. So at a specific node where we have some input X and some output Y, we can directly compute the gradient dy dx. And what we call it is a local gradient. We call this a local gradient because it is local to this node over here. Similarly, let's say we take one step forward. We use this variable y, and we get this variable s at the end. Now, if I want to compute this immediate gradient of ds dy, I just need to do this hop, and I just need to look at this immediate gradient of ds dy. And the fact that if this is our target node, this gradient here of ds dy, we call it the upstream gradient. Upstream because it's coming from a later part of the operations. Similarly, let's take one step backward, right? We have some function z, some variable z, we pass it through g and we get x. Now, if I want to compute the immediate gradient of dx dz, I just need to do this immediate hop, and out comes the gradient dx dz. And if we again consider this the target node, the fact that it comes before the target node, we call this the downstream gradient. So we have three types of gradients: downstream gradients, local gradients, and upstream gradients. So how exactly does backpropagation take place using these different types of gradients? Using the chain rule, we can kind of combine the downstream, local, and upstream gradients together to compute the gradient of this s with z, or s with x. And to do so, we get something like this. I have my upstream gradient over here. I have my local gradient over here. And finally, I have my downstream gradient. So we can generalize this to a higher level, that any gradient in your computation graph, it can be represented as a product of the upstream gradient, local gradient, and downstream gradient. And you can do this using our best friend, the classic chain rule, simple multiplication of these individual gradients. So now that we have looked at the whole, different types of gradients, how do you view a neural network as a computation graph, or rather, how can you represent a neural network using a computation graph? Let's look at specific instances of neural networks, all the way from a single perceptron, meaning a single neuron, all the way to something like a 2-layer network that you've seen in your tutorial 8 last week. And we're gonna do like a walkthrough of how we solve them, or solve such problems. So just give me a second. Okay, yeah. So let's say that we're dealing with a single neuron. And I call this a neuron because it's a synonym for a single perceptron, meaning it looks something like this guy over here. You have a single node, you take in some input x, you pass it through function f, and out comes a prediction y. Very straightforward. This is like saying, like you're doing linear regression or logistic regression. A single perceptron unit is similar to logistic or linear regression. It's just that the difference is what activation function you use. It's pretty straightforward. So let's abstract this perceptron using the functional method that we've been doing so far with computation graphs. Let's call it function f. That means my prediction y hat, it's this function f of my weight, of the input, and my bias. And I can do it something like wx plus b. And as with all supervised learning problems, we have some loss function L. It takes in my prediction and my label, and it spits out this individual real value. It spits out a real value of this error E. And the whole deal with backpropagation and gradient descent is that we want to find the gradient of the loss, or the gradient of the error E, with respect to the parameters W and B. So this guy and this guy. So let us look at the computation graph perspective of this single perceptron or single neuron. We can view this like so. We have our individual variables w, x, b. We pass it through this function f to get y hat. And finally, we pass it through the loss function or the cost function L to give me my error E. So now using this concept of the three types of gradients, let's do exactly this process. So now let's say we are computing the gradient of E with respect to W, so this guy and this guy over here. So to do that, I need to go back. I need to back propagate through my computation graph, which means I need to go from here one step behind, and from here I take one step behind here. And finally, I reach my destination of W. And all we need to do is we need to take the gradients that fall along that path. So that means I need to take this guy right here and this guy right here and multiply them. And I finally get the gradient of the error E with respect to W. Classic chain rule. And one thing that you can notice is that, sure, we have these local gradients, but on this end over here, we have no upstream gradients. And in the situation where there is no upstream, when there's no upstream gradient, you can just count that as one, right? One multiplied by anything is that number itself. So it's as if there's no effect. So the upstream gradient is present, but it has no effect. Similarly, when we look at this other end, the backward end of this, there is no downstream gradient, right? There's nothing coming from behind. So you can also count this downstream gradient as a one, and anything multiplied by one is the thing itself, no effect. And we have local gradients. So again, we can compute the gradient of the error E with respect to B, and out comes this chain rule to get the gradient DE dB. And you may be wondering, okay, Rish, so far we did it pretty plain and simple with this y equals wx plus b, but a lot of my questions in my tutorials or even future exams, they're going to have activations, added complexity, right? How do we do this computation graph method for activations? It's pretty straightforward in saying that you have this, right? Y hat is equal to sigma wx plus b, and this sigma is any arbitrary activation function. So what you can do is you can break down this entire thing into two sub-functions, into something smaller, something more digestible. You can first break up this inside part by saying that z, you make up this variable z equals wx plus b. And similarly, you can take this z, pass it down over here, and y hat now is the sigma or the activation of z. We've broken this single very long function over here into 1 and 2. And similarly, we can represent this as another computation graph. It's just that now I have this intermediate node which represents the function sigmoid or sigma, whatever activation. And now if I want to compute the gradients of E with respect to W, I need to go back. I need to back propagate through my computation graph. I need to 1 hop, 2 hop, and finally I reach it and I reach the destination. And all I need to do is take the gradients that lie on that path. So this guy, and this guy. And I finally get the chain rule to get this gradient over here. And of course, a similar practice, it's just that, I go here, but this time I go under here so that I can use this, and this, and it'll give me the gradient of E, error E with respect to the bias B. So that's how you do it for a single neuron using the computation graph approach. Now let's do another quick check-in. Right, we've gone through Backprop and we've done Backprop for a single neuron, a single perceptron. Does anybody have any questions? I'll give you 10 seconds to kind of either type it or unmute yourself. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Again, you can always ask it during the Q&A panel at the end. So now let's move on to something more complex. Let's move on to a single layer. We worked with a single neuron, single perceptron. Now let's generalize to a single layer. Let's go one step higher. In machine learning, or at least deep neural networks, or the multi-layer perceptron, we have this concept of layers. What exactly are they? You get a layer when you take a single neuron and you stack it vertically one on top of the other. So in this case, all of these guys, they form some layer L1. And if I have one single input, I'd be kind of copying this input so that it would go to each of these individual independent neurons or individual perceptrons. So it's like saying X1, I pass it through perceptron 1 and I get Y hat 1. Then I take X1 again and I pass it through perceptron number 2, and out comes this other thing, and all the way till some n, and out comes this. So I use the same exact input. It's just that based on the parameters that are there in each of these individual neurons, you get your corresponding output predictions accordingly. So that means each perceptron has their own value of this W and B parameter. And of course, this is supposed to be B4. Yeah. So it's very independent, very isolated. We're just doing a repeated computation so that we can increase the representation power or the learning power of my model. So I want to introduce you to this concept of vectorization. So far, we've been working with single values, real values, like 2.6, 1.5, 3.2. Those are scalar values. Now we want to take those scalar values and we want to stack them up. We want to create a vector, and a vector is basically a vertically stacked bunch of scalar values, elements. So for the single input, we had 5 different sets of these parameters W and B. Now let's say I have 5 inputs. That means I have X1, X2, X3, X4, and X5. All of these are the features, input features of some problem. X1 could be, X2 could be the crime rate in the area, X3 could be kitchen size, X4 could be the number of rooms in the house, and X5 could be parking lot space, right? Let's say we have 5 input features. So for each of these 5 input features, they themselves would have 5 independent sets of this W and B, which means altogether, I'll be having 25 sets of this weight pair, X1 to X5. So it's something like multivariable regression. You've already seen this, and you've actually done something like this for your problem set 4, and even in the lecture and tutorial. So it's like saying, I want 5 different independent, randomly generated copies of my parameters W and B. And the nice thing about it is you can stack all these parameters W in a matrix. So again, just kind of like a quick recap, we have 5 inputs corresponding to 5 features. We have 5 neurons over here, and each of them are taking the same exact copies of the same input. Each of these different colored lines, they have their independent values of W and B. And, of course, you can kind of sum them and average them to get your final prediction of Y hat. So this would be doing a single layer. You take your inputs, pass it through a single layer, and out comes a prediction. So yeah, so if you had to think about it using the computation graph analogy, every set of parameters in this layer it has its own mini computation graph. It's taking its own value of x1 or x5, whatever, and it's giving out its own y hat value. So it's its own tiny computation graph. But you do this many times in parallel. So now let's say that we have a single instance, a single sample, and this sample has some n features. So x1 all the way till xn. Similarly, x1 could be square footage, x2 could be crime rate, xn could be kitchen size, whatever. And suppose I have m of these samples. But let's ignore this part for now, right? Let's ignore this. And let's just look at a single x. It has features 1 through n. So each feature has an associated weight. It looks like this weighted sum of w1 x1 plus w2 x2 all the way till wn xn. This is basically like doing linear regression for like some n number of variables or inputs. So let's stack them up, shall we? We have this input x. We can stack these features x1 to n as a vector. So that would be x1, x2, all the way till xn. And now my w, remember that I mentioned that each input has its own set of parameters, and the fact that we can represent it is some matrix, right? So this matrix would look something like this, where each kind of row corresponds to a specific set of weights that are associated with one of these features x1, x2, xn, and of course for all of these. This number d, like this dimension d, we call this the embedding dimension, and of course n over here, it represents the number of features. So we're taking a vector of size n. When we multiply it by the weight matrix w, it'll become a d by 1 vector, right? And we know this by the simple laws of linear algebra, and I'm sure you've done your linear algebra mods in your previous years. So now that we know this, let's look at a simple case of a 2-layer network. And my 2-layer network, it's pretty simple. I've removed the activations just so that we can kind of get a clearer picture, but the same exact rules apply. Now, let's say that I have 2 layers where I compute Z1, and my second layer, this is my first layer and second layer, computes the prediction y hat. And using this prediction, I pass it through my loss function L, and it should give me my error E. And for the sake of the argument, let's just say that I have a very simple loss function of y hat minus y. That means prediction minus label. So if we had to look at it from a matrix multiplication standpoint, I would be taking my weight matrix, multiplying it with my inputs, adding my bias, and I would get this intermediate vector z. Next, I take this z and make it my new input. I multiply it with my second layer parameter or weight matrix w2. I add my bias 2, and out comes my final prediction vector y hat. And of course, they have their own corresponding dimensions, and they all commute in matrix multiplication by the laws of linear algebra. So now that we have a 2-layer network, for the sake of simplicity, let's say that we ignore the bias. Let's just work with the weights, because if it works for the weights, the same exact gradient computation, it's the exact same for the biases B1 and B2. And the fact that we have 2 parameters, W1 and W2, it means we have 2 types of gradients to compute, DE, DW1, and DE, DW2. And of course, this E would be a vector, which is represented by y hat minus y. And of course, this W1 and W2, they would be matrices. So instead of working with numbers, and numbers get very confusing because you don't know where each number is coming from, let's work with algebra instead. Let's work with pure variables. So let's say we have this problem. It's the same exact network. It's just that now I represent everything as very tiny vectors and very tiny matrices, square matrices. So I have my input X, I have my labels Y, I have my first layer parameters W1, and I have my second layer parameters W2, and it corresponds to these individual values. They're all scalars. You can think of them as individual numbers, doesn't matter. So now let's take this one layer at a time. Let's do the operation Z1 equals W1 transpose times X. So if you take this W1 matrix and you transpose it, you get this guy over here. And if you multiply this transposed weight matrix with X1 and X2, or this vector X, you do this row by row computation. So the final output would be W111 X1 plus W121 X2, and similarly W112 X1 plus W22 from layer 1 of X2. And I get all of these values from here, and these inputs X1 and X2. So now we've done the first layer, and in terms of this diagram, we now have this guy right here, which corresponds to this 2x1 vector. Because we're doing an addition, this entire thing collapses to some scalar A, and this whole thing corresponds to some scalar B. They're all just real values, and you get this 2x1 vector. Let's move to my second and final layer, where I do y hat is W2 transpose times X1. So, sorry, Z1. So I take my Z1, I pass it all the way till here, over here. And that means taking my parameters here, doing a transpose, and it'll give you this transposed weight matrix. And I need to take my Z1, which corresponds to this vector, this exact thing that we computed, we just kind of pass it down into the next layer. And all we need to do is we need to take this, we need to take this value, multiply it with this. We take this and multiply it with this. Similarly, we take this bottom number here, multiply it with this, and this other number, multiply it with that. So it's like saying W211 and W221, and similarly W212 and W222. And of course, you can see that it's getting a bit complex here, and that's perfectly okay. We're dealing with algebra, so things are going to get pretty long, kind of elongated, but it's okay because it's going to start making sense very soon, if it hasn't already. All we're doing is we're doing basic linear algebra operations, basic neural network operations. It's just that we're working with these variables instead of the numbers that you worked with for your tutorials and the worked example with Prof. Ben in the lecture. Now that we have our final y hat vector, again, this is a 2x1. This whole thing kind of collapses to a single number when you do the addition and product. Second, similarly, this entire thing, it's another number when when the dust settles, it's all just two numbers. It's a 2x1 vector. Finally, let's compute the loss E, which is given by the kind of the lame loss function of y hat minus y. And y corresponds to this over here, y1 and y2. It's a 2x1 vector. And since the loss function is given by y hat minus y, we just need to take this y hat, plug it into this, something like this. And we're doing this this difference, the subtraction based on our loss function here. And we can abstract this, this entire difference when all things are said and done, it collapses to this 2x1 vector E1 and E2, which corresponds to the individual errors. So what we've just done so far is we've done the whole forward propagation for a 2-layer network, and we have kind of computed this final loss E1 and E2. So if we had to represent E1 and E2 as a very large function of everything that we've done so far, we can write it like this. E1 is the difference between my, okay, sorry, I think I made a slight error. It's supposed to be y minus y hat, right? Yeah. So because the labels are here and the predictions are here. So my E1 can be represented as my prediction Y1, or sorry, my label Y1. And you subtract output Y hat. And similarly, this E2 variable, you can write it similarly as a difference between label Y2 and my Y hat 2. And now we've basically written E1 and E2 as a whole kind of set of operations. It's one huge chain, and we can easily compute the gradients with partial differentiation. And the thing about partial differentiation is that if I'm using something as a target variable, I treat every single other variable as a constant. So let's say that I want to calculate the gradient of DE2 with DW111, right? I want to compute the gradient with respect to this thing that I'm highlighting over here. All I need to do is I need to treat this one as a constant, this as a constant, this as a constant, this whole thing as a constant, this as a constant, this as a constant. And I can directly compute this gradient and it should give me something, right? It's a pretty straightforward algebra thing. I'm pretty sure that all of you can go ahead and partially differentiate this, or even straight up differentiate this in a pretty straightforward manner. So in terms of the gradients, we were originally looking at this. We were originally looking at DE DW1, and you can break up DE, or you can break up this error E as a vector of E1 and E2. So that means, DE1, DW1, DE2, DW2. And the fact that W2 is a matrix, and this matrix has 4 parameters, 4 elements in it, corresponding to, this thing over here and this thing over here, it has 4 elements. That means I'll have 4 gradients that I can compute. So this guy over here, which corresponds to DE1, but now I'm looking at a specific element. So if I had to say 1, 1, 1, 2, 2, 1, and 2, 2, this gradient would correspond to this value. This gradient would correspond to this value. This gradient would correspond to this green thing here. And finally, this purple gradient would correspond to the value here. And you can do the exact same thing for E2. And you have these other 4 gradients that you can compute. And again, use the same formulas as done over here. Similarly, now we're working with our second parameter matrix W2. You can kind of break this down, decompose it into kind of something smaller based on E1 and E2, right? So E1 and E2. And since W2, again, it's a matrix, W2 is equal to W2, 1, 2, W2, sorry, 1, 1, 1, 2, 2, 1, and 2, 2. This green gradient corresponds to this yellow gradient corresponds to this, orange gradient corresponds to this weight value, and finally this purple gradient corresponds to this. And similarly, when we're working with this E2, we can compute the same exact gradients with respect to the weights in this second layer. And with that, that kind of brings us to the end of the backpropagation for 2 layers. It was very abstract. We're working with algebra here, algebra and pure calculus, multivariable calculus. I've avoided the numbers, but you can easily substitute the numbers inside this. Maybe even use your tutorial 8 question. If you had any difficulties with that, do what I just did. Use algebra to kind of abstract it. And all you need to do is plug and play with the numbers, and you'll get those exact gradients that were required of you in tutorial 8. So that would be my strategy or my advice to you if you found tutorial 8 very challenging. Now, the final component that I want to talk about here is backpropagating activations, more specifically ReLU. I received quite a few questions during my tutorial, and the teaching staff received a lot of questions during theirs, where we got this question of, okay, ReLU is this conditional thing, right? If X is greater than 0, if it's a positive number, I just return this X. But on the other hand, if my X is negative, I just return this 0 as is, right? So you can write it as max of X and 0. Just another form of writing it, pretty straightforward. It begs the question, what exactly is the gradient of ReLU? And I'd like to point you to this thing that I call conditional gradient. And over here, this forward pass, it's conditional as well. It has condition number 1 and condition number 2. Similarly, with the same exact conditions, you can get the gradient of this ReLU function. And you have to, and it corresponds to 2 conditions even for the gradient. So that means we can break up the condition into 2 parts. The condition that X is greater than 0, and the condition that X is less than or equal to 0. And if we had to look at that through the lens of ReLU, what exactly is it doing? I have X and 0, based on this condition and based on this condition. Let's look at these individual things as a broken up function. So for starters, let's assume that my new version of ReLU, for the sake of the argument, is ReLU X is, it just returns X. Straightforward, just spits out the same input as the output. This is pretty straightforward, because if I say Y equals X, then dy dx will be equal to 1. So similarly, the gradient of d ReLU dx, that would just correspond to a 1, because I have no other values or no other operations being done. Next, let's look at this second part, right, where I just say ReLU X. So we've already done this. Let's say I want to see ReLU X is equal to 0. So now let's assume that ReLU X is equal to 0. And in univariable calculus, if I say Y equals 0, then my gradient will also be 0, which means this gradient over here, this would basically be 0. So now we have 2 versions of this ReLU gradient. ReLU gradient, right? And on the other hand, we have the second version where this ReLU gradient is a 0. We can kind of combine both of them to give us this conditional gradient, as we call it. For the same exact conditions where X is a positive number and it corresponds to this left case, all I have to do is return a gradient of 1. Similarly, if my X is lesser than or equal to 0, I do what my left condition has told me to do. I just return a gradient of 0. So altogether, you can say that the combined gradient of ReLU, it would give me 1 if for all positive values, and it would also give me 0 for all negative or 0 values. So that means if I have some kind of neural network, ReLU WX plus B, And now if I'm calculating this local gradient of, let's kind of break this down as we did for the computation graph, right? Let's say W equals WX plus B and Y hat is equal to ReLU of Z. And of course, let's say that I have some loss function, it gives me error E, loss Y hat Y. And of course, since we're dealing with this W and B, if I want to compute the error or the gradient of DEDW, I need to use the chain rule. I need to hop back on my computation graph. I need to do DE, DY hat, DZ, and DZ, DW. Computing this and this is pretty straightforward. All you need to do is, well, partially differentiate your loss function. This could be mean squared error, or logistic loss, anything that you've learned in 2109S or beyond. Even this is pretty straightforward because DZ, DW, if we treat everything else as a kind of constant, this would just give me an X. It's this middle part over here, and DY hat DZ, all I'm doing is computing D ReLU DZ, because Y hat is a consequence of running ReLU on Z. And all I have to do is this, right? So that means if my WX plus B value in my forward pass, if this thing was greater than 0, this gradient would be equal to 1. But if suppose my gradient or my WX plus B over here was lesser than or equal to 0, this gradient would become 0, meaning this entire thing would just give me a gradient of 0, because 0 times anything is 0. So hopefully we've successfully kind of broken down this conditional forward pass and conditional backward pass, conditional backpropagation, conditional gradients, and hopefully you understand the gradient of ReLU a bit better. And with that kind of brings me to the end of this whole boot camp. If we had to do a whole overview of what we've covered so far, we have done, we've done computation graph, we've done partial differentiation, we've done chain rule. And all three of these are kind of like your Lego bricks, right? You use them as the foundational building blocks to help you in backpropagation. And once you understand backpropagation, you can backpropagate a single neuron, you can backpropagate a single layer, and you could even backpropagate a 2-layer network, right? And now we've also shown you how to do backpropagation on these very weird activation functions like ReLU that have this conditional thing, and it kind of reinforces how you can do backprop and compute these upstream gradients, local gradients, and downstream gradients, how to put them all together to backpropagate and fully update your network using gradient descent, using this very familiar formula that you've seen all the way from your linear logistic regression chapter. So yeah, so this is how we go about it. Thank you so much for your attention. I will be taking, I'll be taking any questions now. Otherwise, if you have no questions, feel free to stick around or feel free to head out for your other commitments. Thank you so much. Have a great Thursday evening. Thanks. Yeah, thanks for being here.